Here we are in part 2 of basic sampling issues. So let's keep talking about random sampling. So if you remember about sampling methods in general, there are two broad families that we were discussing last presentation. One is probabilistic sampling. The other one is non-probabilistic sampling. We're going to discuss a little bit of both. In the previous video, we talked about simple random sampling and systematic sampling. And what I was telling you is that they have some advantages over non-probabilistic methods, in particular that you can actually make assertions or statements about the population based on the information that you get from the sample. So you can generalize, which is a very important property. The reason why you can do that is because you can use inferential statistics, and all the machinery has been created over about 3 centuries, right? So you can do that. And what we're going to do in this particular presentation is we're going to discuss some more sophisticated sampling methods that enable you to do the same thing that we could do before with the more simple version, but in a more efficient manner. And then we'll discuss also non-probabilistic sampling methods a little bit. Okay? So let's start with stratified sample. Stratified sampling, it's a technique that tries to, as much as possible, improve efficiency over simple random sampling. The way it does this is by a priori, before you sample, partitioning the population into groups called stratas. So a strata is just some characteristic that enables you to partition the population into subgroups. Typical example of this will be gender, but it doesn't have to be. I'm going to give you an example that we have already done in the previous slide, where we have large and small stores. That will be stratification variables so long as you define what large stores and what small stores are. Of course, you could do large, medium, and small, or you can do any other categorization. Okay. Now, the idea with the strata, it's basically to leverage the relationship or correlation, typically, between the variable that you're interested in measuring and the stratification variable. Okay. So, for example, if large stores tend to have more sales, which probably is reasonable to assume, and drawing from a subset of stores that are large is going to be more efficient than just drawing from the general population of stores. Okay, and by doing this, what we're going to try to do, if that relationship is strong enough, is improve the efficiency of our sampling mechanism. Now, this is not intuitive. Okay, so because it's not intuitive, what I want to do is I want to work out some numbers to show you that actually what I'm saying is true. Okay. So let's go through our old example, our old story. We have a population of a retail chain that has 5 stores. That's all the units that are in the population, 5 stores. And we can observe in this case that there are sales that we have recorded using whatever method, right? Observation, right? So we have observed sales, and we also know the square footage of the stores, and based on some arbitrary criteria that an expert in retailing has suggested, we have called stores that are larger than 10,000 square feet large and smaller than 10,000 square feet. We have considered those stores small. So what we're going to do now is come up with a different mechanism to draw in from this population as opposed to just simple random sampling. If you remember simple random sampling, every unit has the same probability of being chosen. In this case, because our population has 5 stores, each store has a chance of 1 divided over 5, which is the population, and chance of being chosen. That is roughly 20%. Okay, let's change that. How are we going to change it? Now we're going to define this strata the way I already outlined it for you. We're going to use the size of the store to create 2 groups. We're going to call large stores to the ones that are larger than 10,000 square feet, small stores to the ones that are smaller than that. And as you can see from the data that we have, the large stores are store 1, 2, and 3, and small stores are 4 and 5. And we're going to leverage this information to draw differently. Let's see how. What we're going to do is instead of drawing from the entire population, right, using some simple random sampling, what we're going to do is we're going to apply simple random sampling to each of the strata separately. So for example, if we want to collect a sample of size 2, what we're going to do is we're going to go to the large stores and draw one observation from the large stores. And we're going to go to the small stores and draw one observation from the small stores. What this is going to do is it's going to enhance the chances that at least one of each of those stores gets drawn. That way we do not get unlucky and either only get a sample of 2 small stores or a sample of 2 large stores. What this is trying to do is it's trying to increase the representativeness of our sample, and by doing so, it's going to increase our efficiency, which is not obvious, but I'm going to show you in a minute. Okay, good. So let's look at how this works. Now, when we try to compute the average for any sample that we draw from the strata instead of from the general population, we need to weight those observations because the probability that we will see one of those observations is not the same because of the size of the strata are different. What do I mean by that? If you remember, out of 5 stores, we had 3 that were large, 3. So the odds that we will see a large store is 3 divided by 5. I'm assuming everybody follows that. So when we're computing an average and we're drawing from these different strata, in this case large stores versus small stores, we need to acknowledge the fact that there are more large stores than there are small stores. So we need to weigh disproportionately heavier the larger strata to make sure that whatever average or guess we came up with is as close as possible to the true value in the population. Okay, so what we're going to do is instead of using a simple average, which I know is what you're used to, is we're going to use a weighted average. And the weights, which you can see over here, these are the weights. Okay, the weights are going to be proportional to the size of the strata. The larger the strata it is, the more we're going to weight that data. The reason why we do this is because we want those data points to be more reflective of the population. That strata is bigger, there are more large stores, so we should count that observation more than the small ones because there are less of them in the true population. Okay. Good. So like I said, it's a weighted mean. And in this case, if we collect store 1 and store 2, remember their sales were 15 and 13. Okay. Instead of computing the straight average between these two, which will be 14, it will be 15 plus 13 divided by 2. What we're going to do now is we're going to use weights for computing the average. And those weights are going to be reflective of how likely are we to observe a large store, which 1 is, versus a small store. Store 4 is a small store. Okay. And those weights are going to be proportional, like I told you, to the size of the strata. There were 3 stores that were large out of 5 in the population. So I'm going to take that large store data point, which I have 15, and I'm going to weigh it by the size of the large strata, which happens to be 3. So 3 divided by the total number of stores in the population, that gives you the weight that you use to get the impact or the contribution that the large stores will have to the total average. And you do the same thing with the small store. But of course, that weight is going to be diminished. It's going to shrink to 2 divided by 5. Why are you dividing by 5? At the end of the day, we want an average. So we'll end up dividing by 5 because that's the total size of the population. Notice if I multiply this by 3 and I multiply this by 2, it's the same as adding 3 times 15 and adding 2 times 13. So in the end, what we're doing is we're computing an average or a pseudo average with 5 observations, even though we only have 2. Okay, we have 2, but we're weighing them. We're multiplying this by 3 and we're multiplying this by 2. And then in the end, we divide both by 5. Okay, so that's how we're going to compute the average. This is called a weighted average, by the way. And that's an important concept I'm assuming you've seen in stats before. So let's try to go down through an example where we draw a sample of size 2, in this case 2 stores, 1 from the small group strata and 1 from the large group strata. Okay. So the idea here is, can I compare my results between stratified sampling and simple random sampling, which we have already done? That will be in part 1 of this video, okay? And hopefully show you that actually stratified sampling is more efficient. Now, remember, to compute averages when you're stratified, you need to weigh the data points by a ratio that is going to be the number of people, or in this case stores, that are in that strata divided by the total units of the population. That way we make sure that whatever we get is representative of the entire population. So in this case, what we have here is all the potential samples of size 2 that you can envision from a population of 5 stores. Okay, so it could be store 1 and store 4, store 1 and 5. Professor, why is there not store 1 and 2? Because remember, what we're doing is we are drawing from each of the strata. So strata 1, which is large stores, has store 1, 2, and 3. Okay, so because of that, when you're drawing a sample of size 2, one of the stores is going to be large and one is going to be small, because you are drawing from each of those subgroups, right? So you cannot have a case where you draw store 1 and store 2. Why? Because store 2 is also a large store, and you are only going to draw one of the stores of the sample size 2 that you have from the large strata, okay, which is stores 1, 2, and 3. So 1, 2 is not an option using this mechanism of selection. Okay, so the options are 1, 4 and 1, 5. Remember, 4 and 5 are the small stores. You also get 2 and 4 and 2 and 5. Remember, 2 also is a large store. And 3 and 4, or 3 and 5. So in real life, you're only going to observe one of these rows. Okay, one of these rows, one of them. In this case, we have them all because I have all the information in the population, which is unrealistic, but it suits the example so that you can see exactly what's happening in the background. Okay, and what we're going to do is we're going to take the sales from store 1, which are $15 million, and the sales from store 2, which are store 4, which are $13 million, and we're going to, instead of just add them, we're going to weigh them. We're going to weigh them by the right weights, and the right weights are the number of units in that strata, 15, which is from store 1. It's a large store. There were 3 large stores in the population, so the right weight to use is 3 divided by 5. Okay, why 3? Because there are 3 large stores. Why 5? Because there are 5 stores in the population. In real life, these numbers are going to be much bigger, but the idea is the same. Here, we're going to do the same thing. 13 is the sales that correspond to store 4. Store 4 is a small store, and there were 2 small stores in our population. So the weight that we're going to use is 2 divided by 5. 2 because there are 2 small stores, and 5 because there are 5 stores in total. And when you do this addition, what you're doing essentially is counting the data point 13 2 times and counting the 15 data point 3 times. And if you count something 3 times, you have 3 data points. And if you count something 2 times, you have 2 data points. 3 plus 2 data points is 5 data points. That's why in the end you divide by 5. That's the way of understanding this. What do you have in here? We have our sample estimate or statistic, which is 14.2. It's a weighted average. Okay. This is what we think is the best guess about what's happening in the population, given a stratified sample 1 for anyway. Okay, and remember, in this case, we know the value in the population. We know that when we collect data on all 5 stores, we get 15.2. And like we've done before, after we compute the error, what we're going to do is square the errors, just because sometimes they are negative and positive. And when we add them all up and average them, we get a mean error of the stratified sample of size 2 that is 1. Now remember, this compares really favorably to what we had in the past. For simple random sampling, the error with a sample size of 2 was more than 2, right? Like you can see here. And because of that, this is much more efficient. So you're drawing the same amount of data, just 2 data points, but you're doing a lot better in terms of error. You have a lot smaller error. So this shows you that it is indeed more efficient. In fact, in this case, this is even better than if you collect 3 observations with simple random sampling. If you remember, the average error in that situation was 1.7, and this is even lower than that. So you can see that stratification, if the variable that you pick for stratification is related to the variable of interest, it works quite well. Okay, you can see that, like I was telling you. Good. Now let me show you with a more realistic example and some computation on how do you go about creating an average when you have a stratified sample. So let's assume that in this case, instead of breaking down the population in 2 groups, so 2 strata, we actually break it down in 4, right? 4 groups. So this could be very large stores are over here. Then you have medium-sized stores, then medium small size stores, and really small stores, right? So you have 4 strata, 4 groups in the population, and you have collected a sample of size 100 for each of these, right? So we have 100 observations for each of those strata. Okay, and once that you have those observations, what you can do is you can compute your averages. I'm not going to look at the variance at this point because we're not discussing that yet. We will discuss this in later chapters. So let's say that I've computed my averages for these 100 observations for each of these groups, and they are 7.2 for the largest group, 5.8 for the next one, 4.6 for the next one, and 3.2. Remember, we have 100 observations each. Now let's see how we combine those to come up with an average across these 4 strata. So for you to be able to compute the average, you always need to know the sizes of the strata in the population. You need to be able to break down the original population into whatever number of groups you have. In this case, we have 4. And as you can see, in this case, we have a population of 50,000. Whether this is large or small, it depends on your problem, of course. And strata 1 has 5,000 units on it, or people. Strata 2 has 25,000. Strata 3 has 15,000. And strata 4 has 5,000. So what we're going to do now is we're going to combine those 4 averages that we got from each of the stratas in a way that acknowledges the fact that strata 1 is a lot smaller than strata 2, in fact 1/5, right? So we need to weight this less than we weight this one. In fact, what we're going to do in all cases is weight by the size of the strata divided by the total number of observations. Okay, so what we're going to do is from strata 1, if you remember, we had an average observation of 3.2 out of those 100 observations that we collected. And now what we're going to do is take the size of strata 1, remember strata 1 is 5,000 people or companies, whatever it is, right? And divide it by the total size of the population, which is 50,000. Okay, and this ratio multiplied by my observation from this strata, which is 3.2. We're going to do the same thing with the observation from strata 2. Okay, acknowledge that there are 25,000 units in that strata out of a total population of 50,000. You're going to multiply then that average that we got from our 100 observations from strata 2, which was 4.6 times this weight, and do the same thing with the other 2 stratas. And when you do this, you'll come up with an average of 5.08. You should actually try to do these numbers yourself and make sure that you are following. Now notice that what this is doing essentially is weight very heavily strata 2 and 3 because they are the ones that are most likely to be seen in the true population. And this is why the number is closer to those than it is to the more extreme outliers, let's say, of the other 2 strata. Now, why should you use or not use stratified sampling? I think the answers have already been outlined in our discussion, but let me just highlight them for you. What are the advantages of stratified sampling? The obvious advantage is that it's going to include data from all relevant subpopulations. We're going to make sure that by random chance, we are not going to get data from only one of the subgroups. We're going to force, by design, to draw data from all subgroups. And that it's important if you think that that grouping variable is related to whatever you're doing, okay? The second main advantage, other than representativeness that I was just talking about, is the precision improvement. Is that for the same number of observations, you're going to get more precise, at least the same, but more precise estimates that you will with simple random sampling. Professor, when will you get the same level of precision as simple random sampling? I'll tell you the case. When the stratification variable is not related at all to the variable of interest, whatever you're measuring, then stratification doesn't do anything. And when it doesn't do anything, you'll get the same result as simple random sampling. So worst case scenario, stratified sampling is as good as simple random sampling. What are the disadvantages of doing all this? First, and probably the biggest problem, finding good stratification variables is not trivial. You need to find something that is correlated or related in general, non-linearly, to the variable of interest. If you're measuring sales, if you're measuring satisfaction, if you're measuring price sensitivity, you need a variable that you can get data on at the population level that is going to be correlated with that is going to enable you to partition the population into groups. That's not easy to do. Okay? And second, you can consider stratifying in multiple variables, but when you do this, what's going to happen is the number of groups is going to get large really quickly. If you stratify in gender and income and I don't know, and zip code, for example, the number of groups that you're going to have is really, really large. So because of that, finding data at each of those little subgroups is going to get eventually harder and harder and harder. So you cannot stratify it on many variables, typically one or two. And then finally, as you can probably guess, it requires expertise that goes beyond typical training, and otherwise you're not going to be able to put this together. And because of that, it's going to be more expensive. Good. Now, special type of stratification is cluster sampling. Cluster sampling is when the variable that you use to stratify is geographic location. So when you use geography or like zip code or anything that has to do with where things are located in space, we call that cluster sampling. Now, the reason why cluster sampling is started, in my understanding, is that a lot of the data collection was done physically, in person. So people will knock into people's doors and ask to participate in a survey. And when you're collecting data like this, using geographic locations for drawing the data is very efficient, because that way what you can do is you can put together all the interviews in the same geographic location. When I say location, it might be zip code, for example, right? That way the person that is going to have to go door to door or office to office is not going to have to drive so much, okay? So that's how geographic location is used for stratification, okay? Now, the main advantage of cluster sampling is that, as you can imagine, this can help you keep the cost of collecting the data low if you're doing in-person data collection, which you should consider under some circumstances, although it tends to be expensive. Okay, so it's more cost-effective to do it like this than to use some other stratification variable, because that way you don't have to be driving all over the place or flying all over the place, whatever you need to do to physically go there to collect the data. What is the downside? Well, there are some potential downsides because geographic location is a variable that can create some confounds. So because of that, interpreting and computing the results might be an issue. But in general, it has similar properties to stratification. Good. And that's as much as we're going to say about probability sampling in this class. There is more, obviously, but we need to stop somewhere. Now, let me tell you a little bit about non-probability sampling, which is what you're going to use for your project. Okay. Non-probability sampling has the obvious caveat that I have discussed, which is that whatever results you get, they cannot be extrapolated to the population because we do not know what is the chance that any of the units has of being chosen from the population. Okay. The reason why we don't know is because you're using non-probabilistic methods, right? So let me walk you through a few of them. The first one is convenience sampling. What is convenience sampling? This is ask, like it sounds, whoever is easier for you to get data from. So it could be somebody that you know, it could be somebody that is geographically close to you, it could be somebody that it's already in your website, right? Something that is convenient. Now, because of how those people ended up there, right? It's not random at all. And there is no good way for us to assess what is the probability that any single person or entity will have of being chosen in our study. Because of that, generalizing is difficult. What is the upside of it? Obvious. It's cheap and easy, right? When do you use this? This typically is used early on the process when you're in exploratory mode, you're trying to see what's going on, you're trying to identify the problem, as opposed to measure carefully to what extent that problem is problematic, right? So in a situation like that, what you're going to do is get quick data, try to identify the problem, and then measure it more carefully at a later stage if you think it's necessary. Okay. Same thing with judgment sample. Judgment sampling is when an expert, meaning you, decides who should be sampled. And let me give you an example of judgment sampling that it's used in marketing all the time. Extreme users, people that use the product a lot, are great people to do in-depth interviews with. Why? Because they have vast knowledge about the area, right? If you have somebody who has 4 different cell phones, 2 for work and 2 for regular life, that person knows a lot about cell phones, right? He or she is using them all the time, knows all sort of operating system and interfaces, etc. So in general, that person is going to be great to get really rich data and opinions about cell phone usage or smartphone usage, right? So when you're doing judgment samples, sometimes the reason why you do that is because you can collect richer, better, or easier data. Okay. When else is used? A typical example of this is test markets, which is when you introduce a product or an ad in a few cities and see how it does, right? Those cities are handpicked by experts by claiming, although it's unclear to what degree this is the case, that they are good representations of what's going to happen in the total market of the United States. Finally, let's talk about the last 2 non-sampling methods that we're going to describe. One is snowball sampling. Snowball sampling is when you basically ask somebody that is typically convenient for you, but it doesn't have to be. You ask somebody to basically contact other people and ask them or collect data from them. It doesn't have to be physically ask. You might be passing a link. You might be observing. Whatever technique it's going to be used for data collection, what you're doing in snowball samples, it's basically use the respondents to collect more data from other respondents in a snowball fashion. By that way, getting a larger and larger sample really quickly without so much effort. The biggest advantage of this, obviously, is that it's very efficient. The downside is that it's questionable how those other people are going to be selected by the respondents. And it's very hard to predict how this maps to the population of interest. When is this used? Especially when you're trying to find very unique and small populations where everybody knows each other, but it's hard to reach. So if you're interested in people that collect unusual items, right? They all know each other because there are only so many of them, right? So you might go to Reddit or something like that to find those folks, right? And if you ask each people in that community to collect data from others, you might be able to map to the entire community really quickly. So if you're interested in really niche populations, snowball samples might be the way to go. And then finally, quota sampling. This is when you essentially set up a minimum percentage of a particular variable or characteristics that you think should be represented in your data. Quota samples are used all the time in real market research firms in conjunction with stratified sampling, okay, in some sort of hybrid approach. And that quota is usually set for known variables in the population, for example, gender or income or age, right? If you go to the BLS and you go to the Census Bureau, you can get very accurate data in the United States for things like salary and income or age. So we know a lot about that. So you might use those to make sure that the data that you're getting from your stratified sampling is close enough to the total population of the United States, if that's your target variable, sorry, target population of interest, right? Now, the downside with quota samplings, again, is that you're going to throw away observations that do not match the quota that you've been given. Anyway, that's what I have for right now. Remember, for your project, what you're going to do is mostly convenience sampling by asking people that are relatively easy for you to reach so that you can collect some data. Anyway, we're going to stop at this. Have a good one. I'll see you in part 3.